This video is a continuation of the first part on recursion or recursive problem solving. Here I wish to detail the steps much more elaborately and neatly and clearly so that it can be applied. Also, having made the first video, it made me think if recursion is indeed such a universal and a catch-all technique for or method for solving almost all computing problems, then I must be able to solve it, use it to solve, say, the problem I was working on right now, which was to try to compactly code a string, ordered hashing. Or so before, so first I'll reiterate and detail the steps more clearly again. The first step we have to do is, first thing we have to do to solve a problem recursively is to assume that the problem has already been solved. Has already been solved for the most general case. So this is the first step. Now the second step, actually there are two parts to it. In the second step, part A is, you can call it problem decomposition or break down the problem. Part A of step 2 is break down the problem. Which basically means express the larger, more complex main problem in terms of one or more smaller simpler similar or related subproblems. This is the part A. First part of step 2 is break down the problem decomposition. Now step B, second step itself has two parts. First is problem decomposition. Second step is part B is solution composition. Build up the solution. Had basically emphasized more on building up the solution. That is what is actually most important, which is express the solution to the main problem in terms of its solution to its subproblem. In terms of its solution to its subproblem or subproblems, all the while assuming that the subproblems are also already solved in a like manner to the main problem. This is the second part. This is the most important part. The third one is solve the problem for the simplest base case. So, like I said, having made the video, I started thinking if recursion is indeed such a universal technique which can be used to solve almost any problem, then I must be able to apply it to solve even the one for ordered hashing. So we shall take another example here, which is for ordered hashing. Now when we try to hash information, what we notice is that if we have to preserve order, we invariably have to go from right to left, the way we add up numbers and stuff. So if we try to do that and then we try to add or incorporate, say, another byte of it or something more information from this side, we will always find that we will lose information from the other end. This is what we always encounter. Now the objective, of course, generally the thinking would be to try and decrease the information that is to be coded, which is the key, by as much as possible, while increasing the size of the code itself by as little as possible. So that would be the general thinking. So with that in mind, and assuming the same recursive approach, couple of ideas I came up with was, assume that we are to code a number m equal to 2 power l dash in a value as a value v less than s equal to 2 power l, where l dash is significantly larger than l. Now assuming that I have already coded the value to a certain extent, say from here up to I minus 1 symbols here, bytes or symbols. Then if the v dash is a new value that must be obtained by adding another symbol less than b, digit or symbol less than b, then clearly we would require v dash power I minus 1 by I must be equal to v, and v dash minus v power I minus I by I minus 1 must be equal to d. D is the previous symbol, or if you are hashing, coding it from left to right. So this is what is basically required for us. And this is valid, this will be valid or feasible only if and only if v power I by I minus 1 plus d whole power I minus 1 by I is less than v plus 1. In other words, v power I by I minus 1 plus d is less than v plus 1 whole power I by I minus 1. That is v plus I, v power I by I minus 1 plus d must be less than v power I by I minus 1 plus I by I minus 1 times v power I by I minus 1 minus 1. In other words, so this is the requirement. So v power I by I minus 1 will cancel out, and we will be left with d must be less than v. It will actually be d must be less than I by I minus 1 times v, which is, now the assumption we have made here is if we hash add a new symbol to v, the new hash value v dash is nothing but v power I by I plus 1. We would something around that value it should come. And the difference when we unhash it to is the symbol d that we have. That is the trailing symbol d. When the leading symbol is added to v, and then the trailing symbol must come there. That's what is required. We can see that this is possible. In other words, d must be less than v, or we require that value. This is reasonable because if we know that if there are b power I is the value there and a new symbol is introduced to it, this is reasonable because then b power I by I times I plus 1 by I is nothing but b power I plus 1, so it can be reasonably done. But however, this suggests that the value to be added must be greater than the hash value. So instead of starting off the value of I with 1, 2, 3 and all, we can start off with the initial value for the hash itself as a base value, and thereafter assume values of I greater than 1, slightly more than say 2, 3, 4 or whatever, slightly more than 1, and then keep hashing it like this. So this would be reasonable. Another idea that I came up with, which was express the solution to say the larger, if v is the value that has been coded, then C inverse of v minus some value, it need not be constant. We can express it as C inverse of v minus v mod d times s minus d by s plus C inverse of v mod d. When we examine it carefully, we see that this thinking is also nothing but similar to that only. It's not exactly identical. Here we are taking away a certain value and scaling it down to s minus d, and then using it here. This could be very similar. Instead of scaling it down, it could just as well be v power I minus 1 by I. In other words, these two are very, very similar and related, though not identical. Another thing to notice that the value of d itself could be a function of v or v mod d itself. So this way you will have greater flexibility. The third one is probably the most simplest and the common one, and so if we have a value to code a k less than m equal to 2 power l dash as a value v less than s equal to 2 power l, natural thinking is to assume a ratio r is equal to 2 power l by l dash. So suppose we take this as the value for r. It means if L bits are coded there, k value of k is coded as a value v, the value k by 2 must be coded as v by r, is what must be coded. So we can write if we do manage to code k k by 2 as v by r, and then we invert it, then we must be, if we are to preserve the information, then we invert it, then we must have C inverse of v times r must be equal to k. In other words, C inverse of coded value for k by 2 times r must be equal to k, or C of k by 2 times r must be equal to C of k. So C of k equal to C of floor of k by 2 times V of k by 2 times r. Now we can rewrite this as C of floor of k by 2 plus k mod 2 by 2 times r. Now I shall redefine this in a try to redefine it in a more simpler way as C of k equal to C of floor of k by 2 times r plus say f of some value, some function of k mod 2, where 0 is less than equal to f of k mod 2, which is less than 1. Now if we expand this here, we will get C of floor of k by 4 times r square plus C of plus f of floor of k by 2 mod 2 times r plus f of k mod 2. Again, if we are to recursively apply this, in general we can see that it will have a simple pattern C of floor of k by 2 power n times r power n plus f of k by floor of k by 2 power n minus 1 mod 2 r power n minus 1 plus f of floor of k by 2 power n minus 2 mod 2 r power n minus 2 and so on. Now while coding, we must remember that if this happens to be 1 and all of these are zeros, the value that is added must be slightly more than when this happens to be 0 and all of this happen to be 1. In other words, we know r to be 2 power l by l dash. So in order to ensure that a simple function which is based on nothing but successive halves add up to 1, we can write if a equal to log of k, then f of k can be defined as C of floor of k by 2 times r plus k mod 2 by 2 power a minus log of floor of k by 2. So this function can be used to code a string effectively. Another thing we should notice, like I said, we saw in the first example that the base initially we assume a slightly high value, constant high value for the hash, and then use I by I plus 1 by I for increasing the hash value marginally while adding more and more information to it. The same idea can be used, actually much more simpler idea here. If we have r equal to 2 power l by l dash, it could be something else also. Now what we have is, if we have hashed a value say up to a certain maximum value, say s dash, and then we have to hash one more bit, previous leading bit to it. If the value is, what we could do is, if the leading value is 0, we could try and decrease the value of v by somewhere amount, say r dash v. And if we try, or if we try to r dash v or 1 minus r dash v. And then if the value is 1, we could try to increase it to be to whatever is the value s dash plus r dash v. Now if r equal to 2 power l by l dash, then we require 1 minus r dash r dash minus 1 minus r dash must be equal to r, or r dash equal to r plus 1 by 2. In other words, we hash it to a certain value. If the value we wish to hash it to must be less than 2, we can try and decrease the value of the hashed value by a small amount if the leading bit is 0, and also increase it by a small amount if the bit is 1. So that means we also have to start off with an initial constant value, which when decreased throughout L dash will come up to at most 0, not more than that. So this is a simple technique that can be used.